Good morning. My name is Gus, and I'm here to talk to you about after imaging. I have to warn you, though, that this is going to be very boring. Because after the introductory material, I'm going to show you a piece of 4GL code, and then what does the after image file look like after you run that code. So if you're not interested in seeing that, go find something else to listen to. You can interrupt if there's a question. Sometimes I think I'm making sense, but I'm actually not. So who here is using after imaging? How many of you are not, but you're ashamed to admit it, so you put your hand up anyway? Yeah. Well, these days, there is no excuse for not using it, and it ought to be turned on by default. So the whole point of after imaging is to save you from disasters, which it can do. So let me explain how it works, and then we'll go look at the examples. So this part you may have seen before because I've used these same slides in some other talks on other subjects. So there's two types of transaction logs. There's the before image file and the after image file, or after image log. The before image log, space in there is reused, so it's only got information in it from recent transactions, active ones and also recently committed ones. And then after enough time has passed, the space gets reused, so data gets overwritten with new data in the before image log. That's not the case for after image logs, though. That's a continuous history of all the changes that are made to the database. So what gets recorded in both of these logs is a series of notes that are ordered by time. And when there's multiple users using the same database, the notes that they generate are mixed together in time order. There's one note for every change to the database. And some database changes generate multiple notes. For example, you split an index block because the spot where you want to put the key is full. That causes 3 blocks to get updated. So there's 3 physical database changes for one logical change when you're creating a new index entry. Could be. If you don't need to split an index block, then the creation of an index entry only affects 1 block. So what do we have in these notes? Well, you have the transaction number, the storage area that it affected, which block got changed, and then each block has a version number. So every time a block gets changed, for any reason, the version number gets incremented. So there's a note and a version number in the block that have to match. And then after that, there's a whole bunch of information that's specific to the particular kind of change. So for example, if you delete a record, the note has a copy of the record in it. And the reason it's there is so you can undo. And then when you create a new record, it's got a copy of the new record in it. And if it's an index entry, then it's got the key and so on. So whatever is in there is sufficient for 2 things: to undo the operation if the transaction rolls back, and to redo it if you're replaying an after image log or going through crash recovery. So what's in the two kinds of logs is exactly the same thing. They're identical. However, because I'm stupid, the format of the after-image file and the format of the before-image file are slightly different. So even though the contents is the same, I didn't make them the same. And so it's been that way ever since. Oh, ever since version 6.3, when the way the after-image log works was completely redesigned. And I should have redesigned the before-image format at the same time, but I didn't. So that's why they're different.
Gus, can we bring up some more?
You may.
Back in 6.2, you said your after-image buffers should be 1.5 times your before-image buffers.
I did say that.
After 6.3, does that still apply?
Not really, no. However, well, here's the thing. You generate more after-image notes than before-image notes volume-wise, because the before-image space gets reused, but the after-image space doesn't. It expands continuously until the extent's full or reaches its maximum size, and then you go to the next extent. So for certain operations, you get a lot of after-image data. You'll see some this afternoon. So you might want to have more after-image buffers for that reason. But generally speaking, roughly the same amount. But because the note formats are slightly different, what gets recorded in the buffers is also slightly different. So that's a reason to have a bit more after-image space than you do before-image buffering space. Yeah, I know I sound like I'm hedging, right? It depends. But if you make them the same, which is what I usually do, in most situations you're okay. It's only when you have extreme high volumes of stuff, 1,000 users really pushing the database hard, then you might want to have to take a look at how many times are you stuck waiting for an empty buffer to put a note in and increase them if that happens. It used to be, before 6.3, that you got one buffer of each. There were some other things that were much smaller then, too. Like there was a limit to how many database buffers you could have, which was a pretty small number. Okay, so the names of these logs are lies. The before-image log does not contain before images, and the after-image log does not contain after images. They both contain whatever you need to undo or redo, which sometimes that's the after, like when you're creating a record, you need the record that got created. If you're deleting a record, you need what came before, which is a copy of the old record. Okay, so, oops, hit the button too fast. So there's a number of things that these logs protect you from. There was a customer years ago who had a database crash every night at the same time. And it turned out that the cleaning ladies vacuumed the floor in the computer room, and so they unplugged the server, plugged in the vacuum cleaner. So crash recovery took care of that, but it was still a mystery for a while what was going on. Another case, we had a system at Progress in the 6.2 days where all the sales order entry stuff got recorded in our Progress database. So part of the business ran on that database. And one day, the DBA thought he was in the right directory, but he was actually in the directory that contained the database, and he deleted a bunch of files. So the database got wiped out, gone. So because it was on a Unix system, the files didn't actually get deleted, but their directory entries did. So people who were connected to the database at that time could continue working. So all those people that were using the database had no idea what had happened. So what the DBA did was he got last night's backup and restored that. And then he sent a message to all the users saying, hey, I got a little problem. I got to shut down for 5 minutes. He shuts down the database, rolls forward the after image log, starts it up again, and everybody was good to go. And because they all got warned to get off, nobody had work that was partially completed, so they didn't lose anything either. I mean, they didn't lose the last couple of minutes worth of transactions. That is why you need after imaging, among many other things that could go wrong. Okay, so we have this utility that scans the after image file and tells you what's in it. So if you run that utility, you can get a lot of useful information, as well as a lot of information you don't want to see. And that information allows you to figure out a bunch of things. If you have a problem, sometimes scanning the after image file and then filtering the text that's in there will lead you to figure out what's happened. So here's some of the questions that you could find answers to. This in particular, you know the answer, but then you got to find out, okay, which part of my code did I mess up? Okay, so in order to do this, of course, you have to enable after imaging, because there's no utility to scan the before image logs. There is one that the development team uses internally, but it's not in the product. So there is an option in the scan utility to get a verbose scan, which tells you everything. Or if you don't use that, you only get a summary. Okay, so on to the examples. Now, the examples that I'm going to show you, I ran with this test script. So this part of the script tells you how to use the scan verbose utility. And then when you do that, if you create a database and you don't make any changes to it, this is what the output from the scan looks like. So there's this in mem note. So where it says code equals RL in mem, that is the type of note that got recorded. And then there's a RL last mod note. The in mem note is a copy of the transaction table at that point. And that gets used because when you do a roll forward, the transaction table gets updated as transactions begin and end, but you got to have a starting point. So this note establishes the starting point at the beginning of this AI file, and every AI file has one of those notes in the beginning of it. Sometimes there's more than one because there are other circumstances where that gets written out. The last mod note is the date when the database was last changed. And that's also used when you roll forward to establish a starting point. Anyway, so this part of the scan, I'm only going to show you this once. In all the other examples, I've cut that out just to save screen space. Okay, so here's a sample of some of the note types that there are. There's over 100 different note types. They don't all fit on the slide. Okay, so on to the examples. Some of these examples I got from a gentleman named George Potemkin, who gave me some ideas. Here's the test script that runs these examples. So there's a bunch of source files, .ps. So we create the database, add an AI extent to it, and then loop through running all the examples. Now, this part, you don't have to do that over and over again. I did it in this test because I wanted to start each example with a clean, empty after image file. So I do the backup, start the after imaging, turn it off at the end after the sample has been run and we've done the scan. So each scan only has what that one program did. Okay, so the first set of examples, we're going to do some things with the customer table. So here's the first one, simple one. What do you think happens? Nothing. You get nothing in the AI file except for what was in that piece I just showed you with the in-mem note and the last mod note. How about this one? All right, so nothing. So here we have a transaction and a transaction end, but we didn't change the database. So why are there no transaction begin and transaction end notes? And the answer is because the 4GL optimizes those away. So even though you said start a transaction, the 4GL did not actually do it. It delays certain operations, this being one of them, until you actually change something in the database. So when you go to make a database change, it says, oh yeah, but we got to start a transaction first if we didn't do that already. So in this case, we didn't change anything, so the 4GL says, I'm not doing that. Okay, here we go. Now we're going to change something. Only this time, what we're doing here doesn't actually produce any useful result in the database since we're creating a record and then deleting it right away. So here's what you get. Begin the transaction, sequence update, then we create a record, create some index entries, delete a record, then note that here there's another create, a second create. but the program only had one create in it. It had a create and a delete. So what's that from? Anybody know? All right, what it's there for is it creates a placeholder in where the record got deleted. And the reason that the placeholder gets put there is because if the transaction were to roll back, so you want to undo the delete, it reserves that spot so you can put the record back where it was so somebody else can't go take that spot. And the reason that happens is because when you create a record, the row ID gets assigned, and it stays the same through the rest of the life of the record. So if you want to undo a delete, it has to return to its previous row ID. So you have to reserve the spot because the row ID is an encoding of the physical location of the record. Yes? Yes, there is a second kind of placeholder. There's an index placeholder as well that gets used sometimes. Anyway, we're not going to get into the nuances of the placeholders in this session. Okay, so back to our code. Here's our code. Notice that we had a sequence increment as the first operation, but it's not in the code. Where'd it come from? Trigger, exactly. So, if we do this, what do you get in the output then? No sequence update. You're right. You don't get anything else either. And the reason you get nothing is, first of all, the transaction start is delayed. Then the create is delayed. So we don't tell the database about the create. 4GL keeps that in its pocket. And then the delete happens. So the 4GL says, okay, since you're deleting the record and it hasn't been sent into the database yet, I'll forget about the create and the delete. And then, because we didn't start the transaction end gets optimized away, so that's why you get nothing. Yes? Yeah, so if you didn't have a trigger and you didn't have the disable, you'd get exactly the same result. Yeah. Sometimes things get out of hand. All right, so let's look at another variation of this. So suppose now, after we do the create, we want the rec ID or the row ID, same result. What happens then? So no trigger. Here's what you get in the after image log. Why is that? That's because we can't optimize away the create because you said, give me the rec ID. And you don't have a rec ID until the database decides where is it going to store the record. So now we got to send it to the database. The database does a create and sends you back the rec ID. RMDel is the delete, record delete. It's actually a fragment delete. So if you have a record that's fragmented, you get an RMDel for each piece. The reason it's RRM is because a bunch of notes that have to do with records are handled by a piece of code that's called the record manager inside the database. So it has the abbreviation RM, and then index notes have either CX or IX, depending on what kind of note it is. Yes? Oh, misunderstood. All right, so the first RMDEL is because a previously existing placeholder got deleted because the transaction that put it there is no longer active. Remember that this database got created by making a copy of Sports 2000. And the Sports 2000 database obviously has been modified before it got shipped. So, yeah. Oh, you're right. This is the placeholder from the previous incarnation of the database. Anyway, so there's a placeholder that gets deleted, then the record gets deleted, and we create a new placeholder. Okay, now let's look at a few things to do with the order table. So, create an order, assign values to a bunch of the fields in the order record. So when you do that, because we're using an assign here, and we're assigning values to all the fields that are involved in indexes, the create doesn't happen until after we've assigned all the field values. If you did it as individual assignment statements, the result would be different. So here's what you get. The trigger gives us a sequence number, then we create the record, we create an index entry. Then we create some more index entries, and there's a index delete there that's deleting the index entry that was just created. And then we create some more index entries, and then there's a record update. Yeah, so there's several operations that take place because the key fields get updated. So even though we did the assign, the trigger also creates index entries. So the trigger causes the first index entry to get created as well as the record create. And then the rest of what happens is a result of the assign statement. And because the trigger created the record, we get this update after we've assigned all the field values. So this update comes from the assign statement, and the create comes from the trigger assigning the first key value. Now, if we disable the triggers, and then we do the exact same thing, now you get a different result. So now the create happens after all the key fields have been set by the assign statement. So we create a record, create a bunch of index entries, and then we're done. Okay, one more variation on this. Let's say you accidentally put a dot in the wrong place. So now what happens? When you run your crappy code, you get to create the index inserts, and then you get an update. And the update is because the last statement here got separated from the assign. So first all the assign stuff happens, and then you update the record to set the ship date. So you've turned one database operation into two. I have seen some outrageous examples of that in customer databases, where you go look at the database activity and you find there's way more database record operations than they're supposed to be on a particular table. And then when you investigate that, you find out that somebody's dot is in the wrong place. And in one example, the code that had the dot in the wrong place was in an include file, so it got used all over the place. A big performance improvement by taking the dot off. All right, so what happens here? Now we're updating a record, and we're going to make it a lot bigger. So we're deleting a placeholder again, creating a record, linking the free chain and RM chain together with the block that we used. So there's a bunch of chaining operations that happen in addition to creating the two record fragments up at the top. So the first the two creates are because the record's too big to fit in a block. This database, I think the block size was 4K, but I don't remember. And we made the record 6,000 bytes longer. So you'll see these BK notes. All of those kind of notes are either chaining operations or things like raising the high water mark, which is what's happening here. So BK make is creating a new block out of an empty block in the database, and we're also raising the high water mark. So you'll see those overhead operations that are happening in addition to the database updates or creates. So here's some more. We're creating another fragment, doing some more chaining operations, creating another fragment, and then chaining those, and so on. So that goes on for a while, creating all these fragments. Okay, so let's take a look at some other kinds of things. So in the embedded SQL that you can use mixed in with the 4GL, that has the concept of views. So there's schema tables for creating views. And so what happens if you do something with those? Remember that in the earlier example, the create and the delete with no other operations, this all got optimized away and we got nothing. But because it's a schema table, that doesn't happen. Schema tables are handled in a different way from ordinary records. So the optimization doesn't happen. And the reason for that is because the schema operations have to be handled in a different way because you're making changes to definitions in a running database. And while you're making those changes, you have to keep people out of the part of the database that you're changing, so people can't use a schema operation that hasn't been finished. So what happens is we actually record the schema changes in a separate log file, and then at the end of the transaction, those get played back to the database. And before the playback, they get ordered in the right way. So if you're doing a bunch of schema operations and you have updates and creates and deletes and stuff all mixed together, they get organized into the proper order before the playback happens. So you can't, the 4GL interpreter can't do the optimization because it doesn't know what's going to happen during the playback. So that's why you get stuff that can't be optimized away. Okay, how about this example? Again, we're turning off the trigger so we don't get the sequence operation. And then we do a loop creating and deleting a customer. But we're only executing the loop one time. So what do we get? We get nothing. So those operations all get optimized away by the 4GL. It never tells the database about those. So let's do a different variation on this. Now, instead of a do, we're going to use a repeat. But again, we're doing a loop one time. So what happens? Well, now, you get some notes. You get this save point established by the repeat, and so so you get a save point note, but the other stuff gets optimized away. The create and the delete don't happen. But the save point does, and the reason that happens is because the undo that could have happened needs a marker because you could undo only part of one iteration of the repeat. So that doesn't get optimized away. In theory, it could, but it got forgotten about, so it doesn't get optimized out. The other thing is that the transaction actually started in the repeat loop, but it didn't get started in the do loop. How about this one? So here, we're getting the current value of the sequence that the trigger operates on. So the customer number gets assigned out of that sequence by the trigger. So if we go and grab the current value of it, what happens? Nothing, right? Now, what if we do this? You get the sequence operation, same as if the trigger had done it. And in fact, that's all the trigger does is get the next value of the sequence and assign it to the field in the customer record. But since we didn't create a customer record, we don't have that part. We just have the sequence increment. How about this one? Correct, no transaction. You get a sequence increment, but no transaction begin and no transaction end. And that's because there wasn't one. So you're allowed to update the sequence values without having a transaction open. So there are a bunch of notes that can execute outside a transaction. The sequence increment is one, but there's some other ones. Like when there's an after image extent switch, a note gets generated for that. When variable size extents are expanded, then you get some notes for that. And obviously, transaction begin has to execute outside of a transaction in order to be able to start one, so on. So there's a number of operations where there's no transaction. Okay, so how about this example? Well, we have a repeat block. So you get save points because of that. Because in the repeat block, you get sub-transactions, which you can undo separately from the outer transaction. So you get some notes. How about this one? So we start a transaction, create a customer, undo instead of delete. What do you get? Correct, nothing. How about this one? Right, nothing. How about this one? Nothing, right, that's the last example. So here's all the questions that I mentioned earlier. So go home and try it. My slides will get posted eventually, so you can grab whatever code you want out of those, or you can invent your own. And then when you roll forward, the ship is restored. I didn't know Costa was doing that, but there is a couple of other cruise lines also that are using Progress Database. Well, that's how they knew how many people they lost. Questions? Yes, James.
When you did the one where you were filling the character field with 6,000 ones,
Yeah.
it created the blocks for the and so on, allocated the blocks
Yeah.
and so on. So I'm presuming because that's in the before image and the after image, if that transaction is undone, then those blocks will also be deallocated back to empty space?
No. No, that's a good point to bring up. When you undo, not everything that you did is undone. So the expansion of the variable extent couldn't be undone. Nowadays, it's possible to actually do that, but for a long time, there was no system call to shorten a file. So once you wrote into a file, you couldn't undo that operation. So those kind of operations don't get undone. So the high water mark remains where it was, and that RM block that had a record fragment in it remains in RM block. Record gets removed from it, or fragment gets removed from it. And there's no placeholders for the fragments, only for the first fragment of a fragmented record, because that's where the row ID establishes. But it doesn't matter where the fragments go. Anyhow, so there are quite a number of housekeeping operations that do not get undone. Anybody else? Yes?
You undo a delete operation on the record which consists of multiple fragments.
Yes.
Do we create a fragment for every, a placeholder for every fragment?
No, only for the first fragment. There's no placeholders for the following ones. And the reason for that is because the first fragment is what establishes the row ID of the record, and then where the fragments end up doesn't matter because it doesn't affect the row ID. So we let those go wherever the storage allocator decides to put them. And if you undo the create, the fragments go away. So if somebody comes along and uses the space, it doesn't need to be reserved, so it's okay. It's only the first starting fragment that needs to be handled differently. Anyone else?
Why does it matter that the record ID stays the same through the life?
Good question. The answer is, if the rec ID changes, the index entries are all wrong. So if an update were to change the rec ID or row ID, that would require that every index entry get redone. And we don't want to do that. Some other databases handle that differently. So what they do is they put a forwarding note in the original record location that says, record's not here, go look over there. Which has some drawbacks, obviously. But, you know, it's all a compromise and trade-offs. Anyone else? Okay, thank you for coming. Enjoy the rest of the day. Come see me and Mike in the last slot. At 11? Yes. I thought we were at the last slot. Oh, okay. Never mind. Come see us at 11.